Hey everyone, I want to use this video to tell you a little bit about about linear regression. So this is just an intro video. I'm going to talk a little bit about the main idea of linear regression and what we're going to be doing. We'll learn about the technical details a little bit after that. So let me share up the notes and get started. All right. So linear regression, the main idea is that we're going to have some data, and the data is going to be related or unrelated. Mostly we're going to be dealing with related ones, but of course, sometimes you get two variables that aren't related. And when I say related, what I mean is we're going to have data that has two variables, and we're going to see how those variables are correlated. And there's lots of correlations you could have, but the one that we're going to be looking for is linear correlation, or yeah, that's what I want to say, linear correlation. So for instance, let me whip up a whiteboard here. All right, so we might have, so let's say I've got some data here, right? So here's my X and Y axes, and I might have some data values that we would see that, okay, I might have some data values that look like this, right? So X is a variable and Y is a variable, and we are thinking of them. So we're thinking of like this point right here as having an X coordinate and a Y coordinate, right? And so this might be like somebody, like each of these dots might represent a person, and the dot represents, X is their height and Y is their weight, right? And so it's two variables about the same thing. The one we're going to do in the notes a bit later is like midterm test, or excuse me, final exam scores or midterm test scores and final exam scores, right? You'd expect that the bigger the midterm exam scores were, the bigger you would expect the final exam score to be. We'll see how true that is a little bit later. So here's the idea, right? So there's a trend here, right? As X gets bigger, Y gets bigger, and so we might want to try and find a model for this, right? The best fitting model is what we're going to be doing with linear regression, right? So it looks something like this, right? And so linear regression, the actual process of linear regression is finding this line. There's a lot more analysis that goes into it, right? We're going to see how close the points are to the line, how well the line models the data, et cetera, right? There's going to be a lot of details. But the essential main idea of linear regression is, if you have some data, try to find a line that fits it well, and then figure out how well that line fits. So in other words, we're going to use this, like how well the line fits, we're going to use that to determine how good a job we think X does of predicting Y, right? That's the main idea. And then if X does a good job of predicting Y, so in other words, like if we know how tall somebody is, we can have a pretty good guess at their weight, right? Then this line will be our model. It'll be our function for the relationship between height and weight. That's the plan. That's what linear regression is. There's tons of details, and we'll get to the details later, but that is the main idea there. So let's go back to the notes. Yeah, just a few main points here. You've actually done stuff like this a lot. If you think back to your last algebra class, you almost certainly were graphing things, and that's the same idea here, right? There's a relationship between X and Y. It's defined by some function usually, right? Y equals mx plus b being a really common one, and that's the one we'll be using for linear regression. But in algebra, you usually have an exact relationship between X and Y, right? Every X gives you exactly one Y. In statistics, that's not true necessarily. It's probably not true, right? So for this particular X value here, right, this one right here, we might have a couple of different Y values, right? It looks like maybe this line or maybe this point has that X value, and this point has that X value, and this point maybe has that X value, right? And they all have different Y values. And so that's going to be, we'll talk about this all later, but this is, there's only one X value, one of those X values on this line, right? That X value only has 1 point on this line, but there might be several data values that have the same X. So in other words, these would be all people with the same or very similar heights, but different weights, right? And so that's a thing that we have to take into account and figure out how that factors into our model, right? If there's a lot of spread here, what does that mean for our model? And we'll talk about that later. Just a couple details here. There's lots of kinds of regression. You can do regression with any function potentially. However, we're only going to concentrate on linear regression. However, the lessons that you learn from linear regression can be applied to the other kinds, but we're not going to go over those. But there's quadratic regression and log regression and exponential regression and all kinds, really any function you can think of. And when we get to a couple more, when we get a little more detail, I'll talk about, or in a future video, I'll talk about why you might want to do a different kind of regression. So I don't want to spend too much time on exactly what correlation is, but correlation is basically how the two variables in our data are related. How are X and Y related? And like I said, they could be related linearly. And we would say, even though this data right here doesn't follow a perfect line, the trend appears to be a straight line, right? As X goes up, Y goes up by, some constant amount, approximately. Now, if you happen to know a relationship between X and Y, for instance, let's say this was height and weight, turns out that relationship is not actually linear, right? As your height goes up, your weight actually goes up by a factor of your height cubed, believe it or not. I'll let you think about why that is. You biologists and physicists might have a good explanation for that, but I don't want to get too off track. But if you happen to know what the relationship is, or what relationship you're expecting to see between X and Y, you might want to use that function, rather than just defaulting to a line. However, when you don't want to, when you don't want to assume a particular relationship between two kinds of data, or between the two variables, most people just default to a line, because that's by far the most common relationship between variables that we see in the real world, right? Linear relations are much more common than the other ones, which is the number one reason why we use linear regression a lot. Sometimes if you just hear someone talk about regression, some social scientist or whatever, they always mean linear. They almost always mean linear. I guess not always. I don't want to generalize too much, but they almost always mean linear regression, because that is by far the most common one, which is the one we're going to be looking at. But there can be other relationships as well. There can also be no relationship. So for instance, if you see a set of data that looks like this, let's say we have this, same sort of shape here, but the data looks like that. I would not say that there's a particular trend in this data, right? As X changes, Y doesn't appear to be, Y is kind of all over the place, right? As X increases, I wouldn't necessarily say that Y was increasing or decreasing. Looks pretty kind of like a cloud. This non-relationship turns out to be very important as well. Knowing that X is not related to Y is often very interesting. For instance, let me give you an example. I told you that later on in the notes, or in one of the future videos here, we're going to do an example where we compare the midterm scores and the final exam scores from an actual class I had. It was a stats class that I taught several years ago. And it's going to turn out that there's a relationship. Spoiler alert. However, I've done this in the past numerous times. with other things aside from midterm and final exam scores. For instance, I tried to use homework score and final exam score and compare them. And I figured, of course, someone does better on homework, they're probably going to do better on the final exam. Not true, as it turns out. Those things are unrelated. That is very interesting information, right? That tells me a lot. I want those things to be related. I want it to be the case that when people do better on the homework, that is to say they learn more and put in more effort, that translates into better scores on the final exam. And it doesn't, at least not any way I've ever tried to assign homework. So that tells me that, one, my homework assignment strategy needs more work. But two, that's also very unexpected information. So sometimes non-relationships are as interesting or even more interesting than relationships, right? A relationship that you were expecting to be there that isn't is pretty neat, actually. So that's another option that we will run into. So just a little bit of terminology here. In algebra, we would call these X and Y, of course. In statistics, we typically call them the explanatory variable, that's X, and the response variable, which is Y. And I kind of like these descriptive names, to be honest. The reason we call them that is we're usually thinking of like trying to predict Y with X. It doesn't have to be that way, but that's often the way you're thinking about it. And so you're thinking of Y as being controlled by X, right? So X sort of varies freely, and then Y is kind of determined based on that. So what we say is the X value, the explanatory variable, explains what happens to Y. Like the change in X explains what happens to Y. And so Y is called, or X is called the explanatory variable, and Y responds to the change in X. So we call Y the response variable. You can just think of them as independent and dependent variables if you like that terminology. You can think of them as X and Y if you like that terminology. Or you can think of them as explanatory and response, which I would actually recommend. Think of them as explanatory and response. It kind of, at least for me, gels a little better in my head when we do that. I think that might be all I want to say about this. I think maybe we'll let me hit linear functions real quick just to remind you of how they work. So we'd say a function is linear if it's of this form, y equals mx plus b. You will probably remember that form. Or its graph is a straight line. So every straight line has a graph that looks like this. Every function looks like this. Every graph has a graph that's a straight line, right? The really important thing that I want to get across about this, I'm not looking to reteach an algebra class here, but the really important thing I want to get across is m. M is super important. It's the most important part of what we're going to do, and it's the slope of the line. Now, the way you want to think of slope, I'm sure you remember slope as rise over run, which it is, right? That's not a wrong way to think of slope, but it's not exactly the one we want here. The way we want to think of it here is X, or M, is how much Y changes when X increases by 1. So in this function, let's go over here. If we have the function Y equals like 2x plus 5. Let me make an XY chart for it real quick. This is going to be really straightforward. I'm sure you've done this a million times, but I still just want to do it. 0, 1, 2, right? So if x is 0, y is 5. If x is 1, y is 7. And if x is 2, y is 9. So when x increased by 1, y increases by 2 each time. And the reason that's happening is because 2 is the slope. And that's the way you want to think of slope. Slope is how much y changes when x changes by 1. This is going to be the analysis that we usually want to use when we're talking about linear regression, right? That's a question we ask a lot, is what effect does x have on y? And that the slope is the effect that it has, essentially. So that's the way you want to think about slope. All right, let's run through this example here. I guess I should at least mention B. B will turn out to be very unimportant for us, actually. Like you want to get it right, but it's not going to enter into our analysis in any significant way. That's the y-intercept. It's the y value that you get when x is 0. That's it. All right. So I want to talk about this this question here just to do a little line review. All right, so Danielle is a plumber. She charges a $75 flat fee to come out to do a job at $100 per hour thereafter. And by the way, every time I do this, someone says, that seems really expensive. That's actually cheap for a plumber. Believe it or not, plumbers charge quite a bit. Let Y be the amount of money Danielle charges for a job, and let X be how long it takes her to do the job. So in other words, X is time, and Y is how much she gets paid, or how much she charges. It's probably not her actual pay. Right, so there's a $75 flat fee and $100 per hour thereafter. Now, the easiest way to handle this is to make a chart. Whenever you are unsure about something, and I'm sure a bunch of you probably already know how to do this exactly, but whenever you're unsure about something, try writing down a few values. Whenever you're unsure about a function, I should say, try writing down a few values that you can get from the description, right? So let's say that she is out there for 1 hour. Charge. So if she's out there for 1 hour, she's going to charge a $75 flat fee plus $100 for being out there for an hour. So she charges $175. If she's out there for 2 hours, well, there's a $75 fee plus 2 times 100, right? So this is going to be $275. 3 hours, $375. So you'll notice the hours go up by 1, and the charge goes up by $100. So that tells me that this is my slope. Right? That's M. So what I've got here is really charge equals 100 times hours plus B. Right? And B is the amount that Danielle charges if she's there for 0 hours, which is to say it's the flat fee. Right? So B is 75. And if we're calling charge Y and hours X, what we get is Y equals 100 X plus 75. That's your linear function, right? So she charges an amount that looks like this. Now, this is not actually how plumbers charge. Usually it's like if you go into the next hour, it's just $100 right up front. Or maybe they charge in half-hour increments or whatever. But if you're doing it in a completely smooth fashion, it would look like this. So the slope of the function is how much she charges per hour. In other words, it's how much Y changes when X changes by 1. So how much the charge changes when the time changes by 1 hour. If I want to know how much she charges if she spends 90 minutes doing a job, why is my mouse not working here? My mouse is failing, pardon me. If I want to know how much Danielle charges if she spends 90 minutes doing a plumbing job, well, time is in hours, so I put 90 minutes into hours and I get 1.5. And then we just put that in for X, right? That's literally all we do. This is going to be a thing that we end up doing a fair amount. But if I wanted to know what Y is when X is 1.5, I just put in 1.5 for X. That's the point of a function, right? If I have Y equals 100X plus 75, and I just put in X equals 1.5, which is how many hours 90 minutes is, I end up with Y of 1.5. This is not times, by the way. This is function notation, right? This is Y of 1.5, meaning I have put 1.5 in for the dependent variable. And so I'm thinking of this guy over here as a number. I know there's a Y, but I'm thinking of this as a number because I'm putting in a number for X. Right, we just plug that in and we get 225. So this says that when she is out on a job for an hour and a half, she charges $225 for it. Very simple. This is going to be a thing we're going to want to do a lot, like when we're making predictions using our linear model that regression is going to give us. And this question is a little bit confusingly worded, but not hard to think about, right? So let's say she's already been out there 3 hours doing some disaster of a plumbing job. How much does it cost for her to spend an additional hour? Well, she charges $100 for every hour. So every additional hour costs the same, right? So it's $100, just like all the other hours. That idea of always being the same amount every time X goes up by 1 means that's a characteristic of lines. Now, if this function was not a straight line, that would not be true, right? How much she charged would depend on where she was on the function. So for instance, here, I know I'm being confusing, so let me draw a picture and show you what I mean. So if I had a function that looks like this, right? Looks like a parabola. Then how much X changes from here to here, right? So this is an increase in 1 hour. So if X increases by 1, Y increases by about this much. But over here, when X increases by 1, that wasn't great, but notice that the change in X is the same, right? 1 here and 1 there. But the change in Y is very different. Right, so how much Y changed when X changed by 1 was different at different points on the function. And that's not true of lines. For in lines, it's always the same. So we've got this straight line here. If X changes by 1 there or by 1 over here, the Y change is the same. Right? I didn't draw it perfectly, but I hope you can see that this and this are about the same. And so that's a characteristic of lines. And that is important, right? If you have that property, then you know you've got a straight line. So I think that's kind of all I wanted to say for this intro video. We can talk a little bit more next time. Yeah, we'll talk a little bit more about patterns next time. But I want to leave the intro video right there. So I'm going to go ahead and stop the video here. Next video, we'll talk a little bit more about some of the details of linear regression, maybe go over an example. All right, I will see you in the next one.